All right, let's do week 6, lecture 1, Cox proportional hazards regression, aka survival analysis. So when do you use this survival analysis? Well, it's when you want to compare the rates of some event between two or more groups, particularly if you do not have equal amounts of follow-up time for all study participants. So the important parts are here, it's rates of things, and you do not have equal follow-up like you did with logistic regression, for example. So, Karate Kid, yes, keep going. So, does court-mandated anger management counseling differ from standard jail for reducing subsequent violence? So let's say over the course of 6 months to do this study, you collect data on 104 men who were arrested for domestic abuse in Sacramento County, and you establish whether, upon adjudication, they are sentenced to receive anger management counseling or they get kind of the standard, which is sent to jail. You continue to follow up with these men for another 6 months past when you stopped enrolling them in your study, right? So 12 total months of study time, but 6 months are enrollment, 6 months are just following people up, you go to enroll. And you record whether they are rearrested during that time for a violent crime of any type. That is, they are recidivated. Your independent variable in this study is going to be the type of sentence that they got from the judge. Did they get the anger management or counseling, or did they get standard jail time? And your dependent variable is violent crime rearrest rate. So purpose of doing this, again, is to assess the relationship between the rate of some sort of outcome variable, that's your DV, and any number of predictor variables. They could be independent variables or covariates. So this is similar to logistic regression in that regard, that you can kind of use anything as a predictor for survival analysis. So you want to compare survival, which is the rate of not experiencing the event, but the reality is that it's called proportional hazards regression because it actually compares something called the hazard, which is the rate of experiencing the event, that is not surviving. But it's kind of negative, right? So they talk about survival instead. And this literally does come out of epidemiology, where they were doing heart transplants and seeing how long people survived. So it kind of takes time into account, which so far the only other thing we've done that's really taken time into account as a factor is time series. Not shocking. So note that what makes this cool and why I bother you with this is that you don't have to have the same amount of follow-up time for all your study participants. So like you don't have to have exactly 6 months of follow-up time or 1 year of following up their driving like we did with the logistic regression. You can follow some people for a long time and some people for a short time, and you get to use all their data. So it is a way of graduating faster because you don't have to just sit around and wait. So some participants can have only a little amount of time that they're followed up. Others can have been followed for a long time. And if people drop out, you can actually still use their data. So that's a big problem normally, is people dropping out of your study. Well, here, if they drop out, you get to still do something with their data, which is cool. So plus you get a cool picture, and you gotta love this. The analyses where you get a cool picture. This one and the one we're doing next week are both cool picture ones, which makes every dissertation better. So here's what we call a survival curve. The y-axis here is the percentage of persons in the group or groups who have not experienced the event of interest. So because I used to be a traffic injury researcher, this is of course about crashing, and so that y-axis is the percent of 16-year-old males who were in two groups, pre-GDL and post-GDL, which you guys know from last week is, or the ARIMA assessment is graduated driver's licensing. So we're looking at whether the percent who stayed crash-free differs between those who were licensed before GDL went into effect versus after they went into effect. The y-axis here is days after independent licensure. So in general, it's follow-up time, how long you follow them up. So the further out, we follow these folks for up to 5 years. And each line represents the survival of a group. And note, they both start at 100%. So, day one, everyone hasn't crashed yet, theoretically. Or day zero. Okay, day zero, everyone hasn't crashed yet. I mean, people literally used to crash in the DV parking lot. So it really is, they don't even survive a day in some cases. So here, the GDL group, that is this group up top, that's the dark black line, they have better long-term survival, right? So a higher percentage of them remain crash-free all the way out to 5 years than the pre-GDL group. And that suggests that graduated driver's licensing stuff actually does a good job or a better job of keeping 16-year-old males from crashing. So your outcome variable, your dependent variable in survival analysis is a little funky. It has two parts. So it has what we call the status variable, and that's something nominal and dichotomous. It's a dummy variable of either a 0 or a 1, right? And 1 is the event of interest. So in that sense, this is a lot like logistic regression. It's got to be coded 0, no event of interest, 1 event of interest. So that should sound exactly like logistic regression to you. Here's the funky part. Oh, sorry. For example, 0's lived, 1's died, if you were studying a death rate. So here's the funky part. There's a second piece to the DV. It's the time that each individual was followed up and during which they could have had that potential dichotomous outcome occur, right? So it's usually done in days, but it's the time at risk is what we call it. So time at risk for the event of interest, which we also call follow-up time. So once you have the event of interest, you're no longer at risk for having the event of interest. So in most things, so that's why it's like time to first crash or time to death, time to recidivating. So we'll talk a little bit more about that in a sec. So it is typically days, and we call that person days. So think of it this way: if we follow, we follow one person for a year, we have 365 person days of follow-up. They were followed up for 365 days. But it's summed across all members of a group. And so if we had one person, 365 people who were followed up for 1 day, that's also 365 days of person day follow-up for a group. So it's additive across the members of a group, and they are sort of equivalent. So usually when we do these write-ups, we report person years, not person days, because person days end up being huge numbers, like millions of days of follow-up and stuff. It gets crazy. So we turn it into years. How do you turn days to years? You divide it by 365.25 because of leap year to get an approximate number of follow-up years. So these two pieces, the status variable and the time variable, together make up your DV for survival analysis. And they allow you to create rates for groups of individuals. So a rate for a group is the number of events that occurred in the group, so the number who crashed, for example, divided by the group time at risk for having the event, so the total time that they were at risk for crashing, for example. So it's just basically the sum of the status variable up top, how many people had the event of interest, divided by the total person time on the bottom. That's what we call a rate. It's a rate per unit of time that they could have had the event. And again, we typically do it as a function of person years, even though we collect the data as person days most of the time. So your independent and covariates for survival analysis, I'll just tell you right now, are exactly the same as logistic regression. You got to dummy code them. If they're nominal, if they're continuous, you can just pop them right in. It's the same. But let me now make it more confusing, because that seems to be what I do, unfortunately. So they can be continuous, or they can be ordinal, or they can be nominal with any number of levels. This is one of the ways that both logistic and survival are superior to linear regression. And again, usually one of your predictors is something you're particularly interested in. It's sort of your primary independent variable, and the rest are covariates if you have other ones. They're things you want to adjust for, but you don't, not necessarily interested. So age and sex, for example, are the ones we always adjust for in epidemiology. as they are so strongly associated with health outcomes, including COVID, by the way. That's one of the things we found. Strongest predictor, age. Second strongest predictor, obesity, actually. Third is sex. So continuous and ordinal independent variables or covariates, you can enter the predictors. They can be entered right in the model. Nothing you got to do. So you don't need to dummy code things that are continuous. For categorical ones, that is nominal ones, you do need to do that k-1 levels of a nominal variable in terms of dummy variables. So it's 1 minus the total number of levels. That's how many dummy variables you're going to have SPSS make for you. So it's exactly the same as logistic. And again, SPSS just does it for you. You just got to pick, do I want the first group to be the referent group or the last group to be the referent group? So the level of the nominal variable that is not represented by a dummy variable is again called the referent level, and the relationships are interpreted in relation to that referent level. So, you know, the crash rate of males relative to females, or the crash rate of blonde hair drivers relative to gray, bald, white hair drivers. So it's that relative comparison thing again. So it's basically Groundhog Day for you when it comes to the predictors, because it's the same as for logistic regression. So SPSS will create those dummy variables for you and enter them all into the analysis instead of the original variables for your nominal predictors. So let's say, for example, you wanted to do that anger management versus jail time study. SPSS will do the following. It will create one dummy variable. And remember that the one that's coded 1 on the dummy variable is represented by that dummy variable. So in this case, you would get, it's not an odds ratio, it's called a rate ratio in this case, which I'll talk about, for anger management relative to jail time. So it represents the parameter that you get in that variables in the equation table, represents how anger management folks did for the DV relative to jail time folks. So why? Because anger management is the one coded as 1. That's why. So the jail time is coded as 0, makes it the referent. And so this would be saying first is the referent. That's what will get you this particular dummy coding scheme. So the results for dummy coded variables are interpreted in relation to how the level coded 1, in this case anger management, compares to the excluded level, that's the one coded 0, which is jail time. And that makes sense because anger management's the new program. We want to know, how's the new program compare to the old sort of standard, just throwing them in jail. So let's look at, so taking time into consideration here is something new. So I want to spend a little bit of time on that, making sure you understand what study participants kind of look like and what they contribute to the study. So here is 5 different participants, 1, 2, 3, 4, 5. Note that 2 of them didn't have the event censored. I'll talk about that, someone who kind of dropped out, and then 2 and 3 both had the event, so they got thrown back in jail, I guess, or they got arrested for a violent crime. So this first person had no event. They were enrolled the very first month, and they were followed for 12 months of time, and they were arrest-free. They never got rearrested for a violent crime. That is 12 total months of follow-up. All right, this next person did have an event. They were enrolled the second month. That's where the dark line starts for them. And we followed them all the way out to here. And this month, month 7, they had the event again. So enrolled the second month, rearrested 6 months later. So they have 1 numerator event in 6 months of time. This person also had the event. They were enrolled the 6th month that we were enrolling people, so the very last month, and they fall for 1, 2, 3, 4, 5 months, and then boom, got rearrested. So they contribute 1 event, that is a rearrest to the numerator of the rate, and 5 months to the denominator. So this is new, censored. Person 4 here was enrolled the first month of the study, meaning they got sentenced the first month of the study, and we got them in our study. And we followed them for 3 months, and then we kind of lost track of them. Let's say they left town, or, you know, another thing that happens is they die. Another thing that happens is they say, I don't want to be in your stupid study anymore, whatever. this person was no longer at risk after 3 months because we didn't know where they were, and so we couldn't tell whether they were rearrested for a violent crime. They could have went to another state or something like that. So we call that a censored event. You still get to use their data though, which is cool. You get to know that, hey, I got 3 months of follow-up time with this person. I don't know if they ever got rearrested or not, but you get to use that 3 months of observation. Normally, in like logistic or whatever, where everyone's got to have the same amount of time, you would have to throw that person out. I didn't get to follow them for a full 6 months, so you toss them out. So finally, we got person 5 here. They were enrolled month 5. They were still rearrest free 8 months later at month 12. So they contribute 0 events to the numerator, 8 months to the denominator. So how do we count this follow-up time? So again, let's take a look at person 1 here. So person 1 was enrolled month 1. We followed them all the way to the end of the study. They provide 12 total months that they were at risk for rearrest. Person 2 was enrolled month 2, and they got rearrested month 7. So they provide a total of 6 months of follow-up time. Person 3 was enrolled month 6. They were rearrested in month 10, so they provide 5 months of total follow-up time. 1, 2, 3, 4, 5. Person 4 was enrolled month 1, and then we kind of lost track of them sometime after month 3, so they're a censored case, and so they still provide 3 months of follow-up time. Like if they had been arrested while they were still in the state, we would have seen it, so we get to use that data. And finally, person 5 was enrolled in month 5, and they made it all the way to month 12 and never were rearrested. So they get 8 months. 1, 2, 3, 4, 5, 6, 7, 8 months of time in that denominator for us. So note, first of all, that follow-up time differs across the study subjects. And also average follow-up time could end up differing across the folks who were assigned to jail versus anger management. And so follow-up time can differ both across subjects and on average across groups. And if you were to get a difference in just the group means, the percents who were rearrested, it could reflect differences in follow-up time if you weren't doing survival analysis. But survival analysis takes into account how much time each person was followed up, and so therefore the group rates are adjusted for that as well. So again, survival analysis takes into account the fact that follow-up time differs across people and groups and makes it not a problem. So let's talk a little bit more about rates and time. There are many things that we want to study that occur over time. So some negative ones, for example, are recidivism, ending up back in jail, getting rearrested, drug use, and hospitalization. These are all things that occur over time and at different rates for different people. Some positive ones are completion of treatment, finding employment, being cured of a disease. These are also things that occur over time, right? So a rate, just getting back to that definition, is in the numerator the total number of events of interest, and then in the denominator the sum of the total time at risk for a group. So the sum of the total of events for the group divided by the total time at risk for the group. Time at risk is called person time, which is weird, I know. It's what it's called, and it can be days, months, years, etc. So sometimes they'll say person days if you're using days, or person months, but it's always person time as overall. So here is the data for that anger management versus jail time study for seeing if it affected violent arrest for rearrest for violence. Let's take a look at the first group, anger management. So in the anger management group in this study, they enrolled a total of 56 people. So the judge assigned 56 people to the anger management group, of whom 23 were rearrested while they were under observation. They were at risk for rearrest while we were watching them. Those total 56 people provided 8,846 days of follow-up time. So 56 people were followed up for a total of 8,846 days, right? And so the rate is the number of rearrests divided by the total person time, but here it's per 100 days. So the formula is 23, number of rearrests, divided by the total time at risk, 8846. And then to make it a rate per 100 person days, you multiply it by 100 and you get 0.26. So what does that mean? So that means for those in anger management, about a quarter of a person was rearrested for every 100 days that the group was followed up. Which, okay, what? We're going to get to that in a sec. These are kind of like odds that, a higher number is a higher rate, but really people don't understand rates that much better than odds ratios, or odds, sorry. So we're going to do rate ratios. So how about the jail time group? So the jail time group, the judge sentenced 48 of them to just go to jail, not get anger management. Of those, 22 were rearrested. They provided a total of 7,240 days of follow-up. And so their rate, if you just divide 22 by 7,240 and multiply it by 100 again, is 0.3. So it looks like their rate, if anything, is a little bit higher, right? We don't know if that's significantly higher than 0.26, the anger management group, or not. That's why we run this test. But that's all a rate is their rate was 0.26 for anger management, and their rate of rearrest for jail was 0.3. So the rearrest rate does appear to be slightly higher for those who receive jail time only. And so to compare the rates, we actually don't compare the raw rates. We do a rate ratio, like with logistic where we did an odds ratio. Same thing here, but we do a rate ratio, which is the rate of the group of interest divided by the rate of the referent group. So here's the little formula. We would do the rate ratio is the rate of those who got anger management divided by the rate of those who got jail time. So it's 0.26 divided by 0.30, and you get 0.87. This is just like an odds ratio. It is a rate ratio, though. It's the ratio of two rates. And I actually find they make more sense than odds ratios, but we'll see what you guys think. They're interpreted exactly the same, by the way. But 0.87, what do you think that means? Well, it means that the group of interest, anger management, had a lower rate of rearrest. But let's go through that formally. So how do you interpret these rate ratios? Pissed off Cookie Monster again. So if the rate ratio is less than 1 and significant, that's important, then the group of interest had a lower rate than the referent. So it's just like odds ratios. If its rate ratio is less than 1, just like an odds ratio less than 1, then the group represented by the dummy variable had a lower rate than the referent. And you can convert it to a percentage using a little handy dandy formula, just like the odds ratios. 1 minus the rate ratio times 100 gives you percentage difference. If your rate ratio is equal to 1, then there's really no difference in rates between the groups. So that is another way of saying if it's not statistically significant, for all intents and purposes, your rate ratio is 1. There's no difference between the group's rates. It's like an odds ratio of 1. That's not significant. If your rate ratio is greater than 1, it means the group of interest had a higher rate than the referent for the outcome. So they were higher, and this is what most of the things were. For example, last year at the odds rate, or last week with the odds ratios, the rate ratios were greater than 1 because we were comparing to bald, gray hair, white hair group, and they had the lowest rates. And again, you can convert rate ratios greater than 1 to a percentage by doing rate ratio minus 1 times 100, which make these things a heck of a lot more understandable. So your rate ratio, again, here it is the rate of the group of interest divided by the rate of the reference. We got 0.87, that is less than 1, so that means the anger management group had a lower rate of rearrest than the jail time group. So the rate of rearrest specifically among those who received anger management was 0.87, the rate for those who just got jail, which has like no meaning to anybody except Uberstat nerds. So we're going to turn that into percentage difference. If you do 1 minus 0.87 times 100, you get about 13%. The rate of rearrest among those who received anger management was 13% lower than those who just got jail. People understand that when you tell them that. They don't understand the 0.87, but you convert things to percentage difference. Aha! Anger management results in 30% lower recidivism, right? People understand that, so we're going to do that in this class. How did we know lower? So, oops, how did I know lower? We know it's lower because the rate ratio itself is less than 1. Okay, so we're assuming it's statistically significant here. So in terms of sample size, you need at least 50 people plus 10 per predictor that you use in your model, and that includes dummy variables. That's all I got for you. So if you got, one predictor, anger management or not, you need 60 total people, right? 50 plus 10 for the one predictor, the one dummy. So your assumptions are independence of events. Each person's in your study only one time. Here's a new one. Censoring is random. So people drop out of your study, but it's assumed that dropping out is not associated with the outcome variable or any of the predictors. So they're not dropping out more from one group than another, and they're not dropping out in a way that's related to the outcome. It's just random. So the continuous predictors are linearly related to the outcome. So this is an assumption just like it was with logistic regression. And if you have to test this, I can show you how to do it. And finally, the one we actually are going to test is the proportional hazards assumption. So this is also a new one. So that's 3 new ones. And the proportional hazards assumption, which is why this is called cost proportional hazards regression, is that differences in survival are constant across time. Okay, so whatever that difference is, it's constant across time. And it doesn't it's wild in the beginning and then it slows down or something like that. It's about the same across time. And we are going to graphically assess that using what are called log negative log survival plots. And we're going to look for quote unquote parallel survival between the groups. So anyway, I'll show you what that means. And that's how we'll check it. So how do you evaluate this proportional hazards assumption? Well, you have SPSS do a plot called a log negative log plot. And this is what a log negative log plot looks like for that GDL study. And what you're looking for is the 2 lines representing the groups. Here it's GDL and not GDL. They don't cross. If they don't cross each other, you've met the assumption they are quote unquote parallel, even though here they're not perfectly parallel. The point is they don't cross each other. So if the LL log negative log lines are parallel, then the proportional hazards assumption is not violated, it's met. Here they are roughly parallel over time. They're about the same distance apart over time. And so here we'd say the proportional hazard assumption is not violated. So here's another proportional hazards log negative log plot, and you can see that the lines cross, right? So gosh, what happens? Well, they're definitely not parallel, and this is a violation of the assumption. The red and blue start out far apart, then they get close together, then they crisscross, they literally overlap, and then they grow apart again, and then they overlap for most of the time out there. And so they are clearly not parallel. In fact, they do cross, and so here the proportional hazards assumption is definitely violated. So this is an example of a violation. And then here we have a plot of how my wife perceives my sense of humor over the course of our relationship. Again, you got time on the x-axis, and you can see that over time in blue, I think I'm hilarious across all years of being together, yet her amount she thinks that I'm hilarious decreases, corresponding with particularly important events like being married and having a firstborn child, and we end up with different opinions of how hilarious my jokes are. So this is not really a log negative log plot, but you can see these lines are parallel. Anyway, it would violate it. So how do you evaluate your predictor variables? They give you something called a log rate ratio, or B in SPSS. The exponentiation of B, that is EXPB, is what it actually SPSS puts on the output, gives the ratio of the rate of the event in one group relative to the rate in the referent group. So it's a rate ratio. And these EXPBs, they are your rate ratios that we talked about earlier, SPSS prints out. And so, for example, if SPSS gives you a B of negative 0.1508, If you exponentiated that using the natural logarithm, you would end up with 0.86, and 1 minus 0.86 times 100 is about a 14% difference in survival of the groups. The group of interest was 14% lower. So we use these sig values to determine if the predictors are meaningful, right? So it's got to be sig less than 0.05 for us to say that a rate ratio is different than 1 at all. And if the sig for your EXPB is less than 0.05, then the rate ratio represents a true difference between the levels of the IV and survival for the outcome. So for continuous independent variables or covariates like age from last week, the rate ratio indicates the change in the DV for a 1 unit increase in the predictor, the independent or covariate. So it's just like age last week. So remember, it was a 3% lower ticket rate for every 1 year older they were when they got licensed. So 1 year increase, 1 unit increase in the predictor is associated with what change in the rate ratio for the DV, 3% reduction, for example. So basically, how do you know what's a more important predictor variable? We'll look for larger rate ratios. So larger rate ratios indicate that IVs are more important for predicting the outcome's survival. So that's it. Let's do a worked example. Looks like we're back to traffic tickets among persons licensed in California less than age 18 during 2017, and we followed them up to May 6, 2019 maximum. So the maximum amount of time that a person could have been followed up was 855 days. That is January 1st, 2017, if they got their license on that day, all the way to May 6 is apparently 855 days. May 6 of 2019. So the independent variable here was the age of licensure. Did they get licensed at age 16 or did they get licensed at age 17? So it's 2-level. And there's that variable in here. You can see people got licensed at age 16 or age 17. One of these is coded 0, one is coded 1. The dependent variable is traffic ticket rate. And traffic ticket rate is defined as 2 pieces, right? We've got whether they got a ticket or not, and then we have how much time each person was followed up, and it's days. So we have, did they get a traffic ticket? 0 is no, 1 is yes, just like logistic regression. But then we have this other piece to it, which is days to get a ticket. So it's number of days that they were at risk for getting a ticket, which means it's the number of days until they got a ticket that we were following them, or we lost them, like we call that lost to follow up. They were censored and we don't know what happened to them, or we stopped actually tracking whether they got a ticket. That is the end of the study. So that column is days until they got a ticket, we lost track of them, or the study ended. Those 2 pieces are what make up your DV. So let's describe the study participants. We've got the age that they were licensed. So in California during this time period, there was a total of 208,355 16 and 17-year-olds licensed. You can see that 140,465 were licensed at age 16. Only 67,890 were licensed at age 17. There's a reason people don't get licensed at age 17 in California. It's because if you wait until you're 18, you don't have to do driver's ed. You're not subject to graduated driver's licensing, meaning you can, when you get your license at 18, you can drive with your buddies immediately, and you can drive past midnight immediately. So a lot of people, like, if you're not going to get it at 16, they just say forget it, and they wait until they're 17. So that's basically 2/3, 67% get licensed at age 16 in California. Only 1/3 at 17. So in this plot right here, we are looking not at numbers of drivers, of which there was 208,355. We are looking at person years. So you will do this during your assignment. You will compute person years by taking their days to ticket, their time of at risk, and dividing it by 365.25. That converts days. There's 365 days in a year, right? They add the 0.25 because every 4 years there's a leap year. So, but just think of it as like 365. So how do you convert days to years? Divided by 365, 0.25. And that'll give you years. So here is actually looking at the same drivers, age 16 and 17, but we're looking at how much time they've contributed. And we find that those who were licensed at age 16, they were followed for a total of 218,576 person years. Ranged from 1 day to 2.3 years, and the mean was 1.6 years. Those who were licensed at age 17 were followed for a total of 101,325 person years. The range was 1 day again, and it went up to 2.3 years. Their mean time years followed up was 1.5. So across those two groups, that's 319,901 total years of follow-up for 208,355 drivers. That is how many years we followed them up until they got a ticket, we lost track of them, or the study ended. And we've converted days to years here because it would just be a huge number of days. So this makes it more easier to talk about. So let's run a crude analysis like we did with logistic, where we're just going to look at those who were licensed at age 16 versus those who were licensed at age 17. We're not going to adjust for any other things. We just want to know, does there appear to be a relationship between age at licensure, 16 versus 17, and their ticket rates? So you go to survival, Cox regression, that's where you get this. And note what I've done here under time. It's two pieces for the dependent variable. You've got to put the time and the status variable. And in the status variable, you have to tell it which level you want to predict. 1 was they got a ticket, 0 was they didn't. So we do tell it 1 is the status that we want to predict. And then we put age in the covariates box. And remember, this isn't continuous like it was for logistic. It's dichotomous. You're licensed at age 16, you're licensed at age 17. And I believe it's actually age, 16-year-olds, the number in there is 16, 17-year-olds, the number in that variable is 17. So regardless, we have to tell SPSS, hey, we want to make dummy variable for this, right? So we click Categorical to do that after we put age in the covariates box. And this is where we tell SPSS how we want the dummy coding done. So this is the Categorical covariates box. I've moved age license over to the box on the right. And here I have made the last the referent. Why? Because if it's 16-year-olds are coded as 16, 17-year-olds are coded as 17, the usual question I would get is being licensed at a younger age associated with higher ticket rates or crash rates. So we want to know how 16-year-olds compare to 17-year-olds. So we're going to make 17-year-olds the reference. So the rate ratio we get is how 16-year-olds compare to 17-year-olds. So again, the resulting rate ratio, because we clicked last and click change, will be the change in ticket rates associated with being licensed at age 16 versus age 17. So SPSS, thank God, tells you how the variables are coded. It's got that categorical variables codings table again, and you can see the group that's coded 1 here is the group that's represented by the rate ratio. So here it is 16-year-olds are coded as 1 on the dummy variable versus 17-year-olds who are coded 0. So the referent, again, is the one that's got a 0. The one coded 1 is the group of interest. So the interpretation of the resulting rate ratio is the ratio of the traffic ticket rate for driver's license at age 16 versus the rate for those licensed at age 17. So how do you interpret the rate ratio? In our variables in the equation table, we get in our SPSS output for age license. And again, this isn't continuous age like it was for logistic. You're just one of two values, 16 or 17. And we said we want this to represent 16-year-olds compared to 17-year-olds. So there's our SIG first up. So there is a difference between ticket rates of 16-year-olds and 17-year-olds because SIG is less than 0.05. And EXPB is our rate ratio. It's 0.812. You might find that shocking. That suggests that the group represented by age license, that is 16-year-olds, had a lower ticket rate than the referent, which is 17-year-olds. This is real. So how to interpret it? Well, teens who were licensed at age 16 had traffic ticket rates that were at about 19% lower. How did we get that? 1 minus 0.81 to, I guess, times 100 is basically 19%. So, and we know it's lower because the EXPB, the rate ratio, is less than 1. So 16-year-olds had traffic ticket rates that were 19% lower than those for teens licensed at age 17, and that was up to 2.3 years after they got licensed. So why do the adjusted analysis including covariates? I mean, I guess the first thought is usually when I show that 16-year-olds have better crash rates or ticket rates, people don't believe it, and so they make you adjust for things. Could this be due to confounding by other variables that differ between teens who are licensed at age 16 and 17? What are some of those? Well, could be that more males get licensed at age 17, so the higher ticket rate for 17-year-olds. Could just be sex confounding, right? Maybe. I don't know, but that sounds, it's a decent enough argument. What else? Well, maybe more 16-year-olds took driver's education. In fact, they're required to, than 17-year-olds, and so the 16-year-olds have lower ticket rates because they completed driver's education, and somehow that magically makes them better drivers. That would be confounding by driver education. And then finally, maybe more teens from out of state move here and get licensed at age 17 than age 16, and they crash more. Because being a non-native Californian, maybe you don't know how to drive in California as well. So we would call that confounding by being a non-native. So we are going to redo the crude survival analysis using sex, driver education completion, and non-native Californian status as covariates. All of those are nominal. This is, again, what we call an adjusted analysis because the effects of age of licensure is adjusted for the effects of these other variables, just like ANCOVA and just like we did with age and sex last week with logistic regression. So let's look at our follow-up time for each independent variable by covariate combination. That's how you know if something is a potential confounder with survival analysis. So what do we have here? We have a cross tabulation where I have tricked SPSS into counting a person not just once, but their total amount of follow-up time. And you'll do that during your homework. You'll see how to do it. Use something called a weight procedure. So 48.2% of 16-year-olds' time was for males being followed up versus 50% for females. Excuse me, 50% for 17-year-olds' time was males. So there was a higher percentage of the follow-up time for 17-year-olds appears to be for males, which is consistent with maybe that's why their ticket rate's higher for 17-year-olds. There's more the follow-up time as males. So, okay, it is significant. There's our chi-square. So there's a real difference between 16-year-olds and 17-year-olds. A higher percentage of the 17-year-olds are male, so maybe that is why they have a higher ticket rate, right? I guess. Again, using weight, now we're looking at what who took driver's ed or not, and it's just yes or no as a function of the independent variable, the age licensed. 98.9% of the 16-year-olds person time was for people who had completed driver's education versus only 98.1% of the person time for 17-year-olds, so fewer, lower percentage of driver's education. So is that real? Yes, our chi-square sig is less than 0.05. That tells us, indeed, a higher percent of 16-year-olds person time is among those who completed driver's education. So maybe that's why their rate was lower, because driver ed magically makes them better drivers, which is totally not the case, by the way, but we're just pretending here. How about, again, using the weight procedure, how about being a native Californian or not? So that's also dichotomous, yes, no. For 16-year-olds, 98.1% of their person time was among folks who were native Californians, and only 97.3 of the 17-year-olds' person time was for non-native Californians, or excuse me, for native Californians. So there is a higher percentage of the 16-year-olds who appear to be native Californians, and maybe somehow you just learn how to drive better in California and less likely to get a ticket. I don't know. It is significant, so it is real. So again, this could be a potential confounder. So let's run that adjusted analysis where we adjust for those three potential confounders. I've left days to ticket in the box up top, but I have added, age license in the box at the bottom, and I've added sex, took driver's ed, and native Californian as covariates. And so though all three of those are categorical, so we will have to create dummy variables for those three as well. So going into our box, our option box, where we can define our categorical covariates, I've moved over took driver's ed, sex, and native Californian to the box on the right. And for all three of them, I've chosen last as the reference. So that means for sex, the reference female, which is coded as 2, so the rate ratio represents males versus females. For took driver's ed, I made the referent, or the last level was 2. They did not take driver's ed, no, and so the rate ratio represents those who took driver's ed versus those who did not. And finally, for being a native Californian, 2, the higher level was not a native Californian, so the rate ratio represents native Californians versus non-native Californians. And let's go ahead and look at the proportional hazards assumption. So you click little box in SPSS, try to teach you on the assignment to get the log negative log plot. Here's what that looks like. So the lines they do grow over time, right? But they never crisscross. So we would say they're roughly parallel. Okay, we're looking for things where they like totally switch sides and crisscross. This is a slow growth over time, which on the log scale suggests a constant change. So we would say the proportional hazard assumption appears to be met here. So again, the two lines never crisscross each other. They just kind of stay constant over time after the initial couple of days. This is consistent with parallel in quotes. So parallel means that they smoothly differ from each other. They typically do grow apart a little bit. So the overall model stats we need for our APA write-up, they tell us whether overall the model predicts variation in ticket rates, just like for logistic, just like for linear. So they're in this table called Omnibus Tests of Model Coefficients at the block of interest. And there's a bunch of stuff you can ignore. All you need is this chi-square, degrees of freedom, and sig. Boom. So using this information, you need it to write your APA paper, basically. And here's your general form for a chi-square where you'd fill it in. And the n is shown earlier on the report. And so for this example, we would write the overall adjusted model was statistically significant, indicating that licensing age and the three confounding variables predicted variability in traffic ticket rates. So this is like that sentence that was in linear regression and logistic regression. And here's where it's filled in: a chi-square with 4 degrees of freedom, 208, 355 sample size was equal to 26,844.13, and P was less than 0.05. So this is that statement that always seems to be there. That's like the model was significant and overall did predict traffic ticket rates. All right, here's our survival plot. Again, it comes from your SPSS output. This is what it looks like when it comes out. Both groups start at 100%. Ticket-free survival drops as a function of time. So as the lines go on, they drop. But you can see one group is higher than the other group. They remain ticket-free for a longer period of time. So that's your 16-year-olds. They start higher and they stay higher than the red line through all time. And so it looks like teens licensed at age 16 have lower ticket rates than those licensed at age 17. And indeed, this is real data. That's really what happens. So at the end of the study, you can actually talk about the percent who were outcome free. And that 73% of age 16-year-olds were ticket free versus only 68% of 17-year-olds. So that's the survival difference. So for the APA write-up, you got to modify those survival plots. This should be old hat for you guys to make them APA compliant. So you got to take this thing on the left with, cum survival, days to ticket, squished together. That thing up top that's not a real title. The key not being within the body of the plot itself. And the y-axis not starting at 0. It's really not APA compliant. You got to turn that into this. This is an APA formatted plot. So again, what do we got? You start the axis at 0. You don't want that title at the top. Survival function for patterns 1, 2 is goofy. You wouldn't put that in a paper. You want to make the y and x axis titles actual words, not cum survival and days to ticket squished together. Make them actual descriptive titles. Get rid of your grid lines and then stretch so that the legend is inside the chart parameter. And again, you'll have to copy and paste it into your APA write-up. But remember, you can look here to see what it should look like. So back to the output. SPSS tells you how the variables are coded. And so now instead of just age license 0 or 1, we've got sex, took driver's ed, and native Californian all in this categorical variable codings table. So for age licensed, the dummy variable represents age 16 versus 17. It's because we chose last as the referent. For sex, the rate ratio represents males versus females. For took driver's ed, the rate ratio represents those who took driver's ed versus those who did not. And then for being a native Californian, the rate ratio represents being a California native versus an out-of-state person. So all these rate ratios are adjusted for the effects of all the other variables. So it's like ANCOVA for everything. So when you talk about the effects of sex, well, they're adjusted for differences in age and taking driver's ed and being a native Californian, etc. Everything's adjusted for everything else in the model is the easy way to say that. So let's interpret these adjusted rate ratios. All right, there's our variables in the equation, and now instead of just one row, we've got 1, 2, 3, 4 of them. So remember, age license represents age 16, so 16-year-olds versus 17-year-olds. First stop, is it significant? Yes, there's still a difference even after adjusting for sex, taking driver's ed, and being a native Californian. It's statistically significant. There's our rate ratio, 0.846. It's roughly like 0.85, right? So it's 15% lower. So first of all, it's SIG. Traffic ticket rates for teens licensed at age 16 are about 50% lower than for teens licensed at age 17, even after adjusting for differences in sex, driver's education, and being a native Californian. So remember, it was like 17% before. So a little bit was confounding, but overall, nope. 16-year-olds still have lower ticket rates. How about for sex? Well, remember, the rate ratio for sex represents males versus females. Is it significant? Yes. And it's 1.526, so about 1.53. How do we interpret it? Well, turn it into a percent change. Traffic ticket rates are about 53% higher for males than females. Not shocking at all. So the took driver's ed one represents those who took driver's ed versus those who did not. Is it statistically significant rate ratio? It is. It's less than 0.05, and it's 1.06. So what does that mean? Well, this is real. Traffic ticket rates are about 6% higher. That's 1.06 minus 1 times 100 for those who complete driver's ed versus those who do not. And indeed, this is reality. Driver's ed actually increases crashes in tickets, believe it or not, but they are about 6% higher. And finally, the native Californians, remember this rate ratio based on the categorical variables coding table represents being a California native versus not. Look at this rate ratio. Well, first of all, it's significant. And then secondly, it's 0.181. It's less than 1, meaning California natives have a lower ticket rate than non-natives. Specifically, 1 minus that times 100 is about 82% lower ticket rate if you're a native Californian than for out-of-state transplants. So they have much lower crash rates if you grew up, or excuse me, ticket rates if you grew up in California. So we do take all the stuff from the variables in the equation table, and we have to put it into an APA format table. So you got your beta, your standard error, your chi-squares, that's your walled, your rate ratio, which is EXPB, and then we do something called a confidence interval for survival analysis. That's that 95% CI for EXPB, lower upper. You just kind of copy those in, rounded to 2 decimals, and I can tell you about what those are if you're really interested in the future. So NESI them over. B is beta, SC is standard error, walled is your walled chi-square. Note that your sig values, you put a star on the chi-square or not. Your EXPBs go into your rate ratio column, rounded to 2 decimals, everything is. And then finally, these 2 columns for your 95% confidence interval, lower and upper bounds, those go into the table as well. And so briefly, what is a confidence interval? It is a range that we're 95% confident includes the real value of the rate ratio. If that range includes 1.00, the sig is going to be greater than 0.05 because it means that the rate ratio could be 1.00. And these are typically included in the APA write-up. It's just another way of doing hypothesis testing. So that is it. Hopefully that made sense. You give it a shot. Hit me up with any questions, and good luck.